A few minutes after the universe begins to cool, a quiet race is already underway. In the bright young fog of matter and light, neutrons drift beside protons, not yet locked safely inside the nuclei that will one day become helium, carbon, oxygen, iron, stone, water, blood, and bone. Some of them will survive by finding a place inside an atom. Others will remain alone for only a little while. Then, without breaking apart like glass or burning away like dust, they will simply change. Before following that change inward, into the hidden rooms of matter, take a moment to settle in. If this kind of slow journey through physics and deep space feels like a good companion for the night, a like, a share, or a quiet subscription helps the channel keep making these long, calm documentaries. And wherever this finds someone listening, whether it is near midnight in a dark room, early morning before the world has fully woken, or some quiet hour between the two, it is enough just to be here for a while. The lights can be dimmed, a fan can hum softly in the corner, the body can rest without needing to hold every detail. There will be quarks here, and stars, and the first minutes after the Big Bang, and the strange way a particle too small to see can help decide whether matter becomes simple hydrogen or something richer. Nothing needs to be hurried. The story of the neutron is not loud. It is not large in the ordinary sense. It waits inside ordinary matter, carrying an ancient rule from the early universe. To understand it, the path has to begin very small. Smaller than dust, smaller than an atom, smaller than the nucleus at the atom's center, where the neutron first appears to be calm. The neutron first appears in the mind as something still. It sits in the center of the atom, tucked beside the proton, with no electric charge and no obvious desire to do anything. Around that small center, electrons form their pale, restless cloud, shaping chemistry, color, touch, and the slow reactions that make life possible. The neutron seems quieter than all of them. It does not pull on electrons the way a proton does. It does not announce itself with charge. It adds weight, steadiness, and depth to the nucleus, then vanishes from everyday awareness. That quietness is misleading. A neutron is not a simple bead of matter placed inside the atom like a stone in a bowl. It is a temporary arrangement, a bound pattern, a small storm held together with such force that, from the outside, it looks calm. When it remains inside a stable nucleus, it can last for times that make human history seem like a passing cloud. Some neutrons in iron atoms have survived since before Earth had oceans, before the first crust cooled under a young sun, before there was any living cell to carry memory forward. Locked inside their nuclei, they have stayed in place while continents rose and fell, while stars moved through the galaxy, while the surface of the planet changed again and again. The same particle, when left alone, does not have that kind of time. A free neutron, separated from the shelter of a nucleus, survives on average for only a little under 15 minutes. In a large group of free neutrons, about half will be gone after roughly 10 minutes. Nothing has to strike them. They do not need to collide with a wall, or burn, or fracture. Their disappearance is written into the structure of the particle itself. A neutron outside a nucleus is slightly heavier than the proton it can become, and because the weak force allows a hidden change inside it, that extra mass can be released. The neutron turns into a proton, an electron, and an electron antineutrino. A neutral particle becomes a charged one, and two lighter particles carry away the remaining motion. This is the first strange truth. The neutron is one of the ingredients of stable matter, yet alone it is unstable. It helps build the long-lived nuclei of carbon, nitrogen, oxygen, calcium, and iron. But outside that shared structure it begins to vanish, almost at once. Its life depends not only on what it is, but on where it is. Matter, at the smallest scale, is not only a collection of objects. It is a set of conditions. The difference is everywhere. In the oxygen atoms drifting through a quiet room, neutrons sit inside nuclei, as if nothing could disturb them. In the calcium of bone, they help make the nucleus heavy enough and balanced enough to exist. In the iron carried by blood, They are part of an older story, because iron is forged in the lives and deaths of massive stars. Those neutrons are not new. Their journey passes through stellar fire, through expanding debris, through cold molecular clouds, and through the slow assembly of a planet. They are older than the bodies that hold them now. They are older than every language used to describe them. And still, if one of those neutrons were somehow removed from its nucleus and placed alone in empty space, the long inheritance would change. The old particle would receive no special protection from its past. It would face the same quiet clock as every other free neutron. The weak force would be able to reach into its inner structure, change one of its hidden components, and set the decay in motion. This makes the neutron feel paradoxical. It is necessary for stable atoms heavier than ordinary hydrogen. It helps hold the architecture of matter together. Without it, the periodic table would be a thin and fragile thing, unable to carry the richness needed for planets, oceans, minerals, and living chemistry. Yet the neutron itself cannot simply drift through the universe as a permanent solitary object. Free protons can last, as far as observation shows, for times far beyond the age of the universe. Free electrons are stable. Photons can cross intergalactic space for billions of years. A lone neutron has minutes. The story begins there, in that difference. During the first minutes after the Big Bang, this difference matters on a cosmic scale. The universe is no longer the dense, hot state from which particles first emerge, but it is still filled with radiation bright enough to break fragile nuclei apart. Protons and neutrons move through that early fire, colliding, changing, finding and losing each other. The neutrons are already under pressure from time. If they remain free too long, many will decay before they can be captured into helium. If they are captured soon enough, they become part of nuclei that may endure across billions of years. The amount of helium in the universe still carries the record of that race. A small particle with a lifetime measured in minutes helps determine the chemical starting point for stars and galaxies. The early universe does not wait with intention. It cools, it expands. The reactions that are allowed happen, and those that are not allowed fade away. Neutrons are caught between decay and capture, between solitude and structure, between disappearing as free particles and becoming part of the first stable atomic nuclei. Later, inside stars, the same theme returns in a slower form. The sun shines because particles in its core can transform through processes that depend on the weak force. The weak force is not powerful in the ordinary sense. It does not bind quarks together with the strength of gluons. It does not reach outward like electromagnetism. Its touch is short, quiet, and rare. Yet because it acts so slowly, stars live long lives. The same slowness that gives a free neutron its minutes also helps give a star its billions of years. The universe is shaped not only by what happens, but by how quickly it is allowed to happen. In the deaths of massive stars, neutrons appear again, no longer as quiet members of small nuclei, but as a flood. When a stellar core collapses, electrons and protons are forced together, and enormous numbers of neutrons are produced. In one outcome, the collapse leaves behind a neutron star, a remnant so dense that ordinary ideas of matter begin to fail. There, neutrons are packed under gravity into a state that has no earthly counterpart. In another outcome, neutron-rich debris is thrown outward, and atomic nuclei capture neutrons rapidly, building elements heavier than iron. Gold, platinum, and other rare metals owe part of their origin to these neutron-rich events, where decay and capture compete in conditions far from any laboratory. A neutron is therefore not only a particle inside the atom, it is a hinge between scales. It connects the first minutes of cosmic time to the interiors of stars, the collapse of stellar cores, the debris of explosions, and the material carried into planets. It links quiet stability to transformation. It helps decide which nuclei survive, which decay, which elements form, and which forms of matter become possible. The calm appearance of ordinary matter hides this dependence. A stone on a table seems solid because its atoms hold together. A glass of water seems simple because hydrogen and oxygen have arranged themselves into familiar molecules. The body seems continuous because carbon, nitrogen, oxygen, calcium, phosphorus, and iron are held in place through layers of structure too small to see. Inside those layers, neutrons help provide the mass and balance that make complex nuclei possible. Their presence is not decorative, it is structural. The visible world leans on them, but the neutron itself is not self-sufficient. That is the thread running through the whole story. The neutron is stable when the right forces and energies surround it. Alone, it changes. Inside a nucleus, it may endure. In the early universe, its survival helps set the abundance of helium. In stars, transformations involving neutrons regulate the pace of fusion. In stellar death, neutron-rich matter helps create the heavy elements. The same particle moves through all these settings, and each setting gives it a different fate. To follow the neutron properly, the path must now move inward. The neutral surface has to be opened, not with a knife or a lens, but with the language of modern physics. Beneath the still exterior are charged pieces, hidden motion, and a force so strong that nothing in ordinary experience resembles it. The neutron looks calm, only because its violence is confined. The old picture of the atom is useful because it is gentle, a nucleus in the center, electrons around it, protons carrying positive charge, neutrons carrying none. For a first map of matter, it gives the mind something to hold. It makes the atom look orderly, with each part given a name and a role. The real atom is less tidy. The electron does not circle like a planet on a neat path. It exists as a quantum cloud, spread across possible locations until an interaction forces one answer from the blur. The nucleus is not a bundle of tiny solid beads either. It is a dense knot of energy, force, and motion. Even the neutron, the quiet neutral piece, is not neutral in the way a smooth stone is neutral. Its total charge is zero, but that zero is a balance, not an emptiness. Inside every neutron are three smaller particles called quarks. They are not smaller balls hidden inside a larger ball. That image fails almost at once. Quarks belong to a stranger kind of matter, where the word inside has to be used carefully, because nothing is sitting still, and nothing can be removed without changing the whole system. For the neutron, the three main quarks are two down quarks and one up quark. These are called valence quarks, the defining pieces that give the neutron its identity. The charges of those quarks explain the neutron's outward silence. An up quark carries a positive electric charge of 2/3. A down quark carries a negative electric charge of 1/3. Two down quarks together carry negative 2/3. One up quark carries positive 2/3. Add them, and the total is zero. The neutron has no net electric charge because its hidden charges cancel with almost perfect balance. This is a quiet but important reversal. The neutron is not neutral because it contains no charge. It is neutral because it contains charge arranged in a way that hides itself from the outside. A particle that seems electrically blank is actually built from charged constituents, held in a pattern so tight that only careful experiments can reveal the structure beneath. For much of early physics, this was not known. The neutron seemed like one of the basic pieces of matter, standing beside the proton and the electron. The atom had already been broken open. The nucleus had been found. The neutron completed a simple picture. And simple pictures are hard to let go of once they begin to work. Then high-energy experiments disturbed that simplicity. When protons and neutrons were struck hard enough inside particle accelerators, they did not behave like smooth, indivisible objects. Collisions produced a growing family of short-lived particles, far more than a simple model could explain. The subatomic world started to look crowded. Patterns appeared inside the crowd. The patterns mattered more than the list of names. In the 1960s, Murray Gell-Mann and George Zweig proposed that many of these particles were built from still smaller constituents. Gell-Mann called them quarks, a strange small name for a deep idea. The proton and neutron were no longer the final layer. They were composite particles, arrangements of quarks bound together by the strong force. At first, some physicists treated quarks as a mathematical way to organize the mess, not physical things that could be said to exist. The evidence grew in the way evidence often does in physics, not by revealing the object directly, but by showing what happens when something unseen is struck. At the Stanford Linear Accelerator Center, high-energy electrons were fired at protons. Some came away at sharp angles, as if they had hit small hard centers inside. The proton had structure. The neutron, by close relation, did as well. The neutral shell had opened. This does not mean the neutron can be imagined as three beads packed together with empty space around them. The quarks are never found alone. They do not sit at fixed corners of a tiny triangle. Their positions and motions are governed by quantum fields, and the particle that appears as a neutron from the outside is the stable pattern of all that activity taken together. The valence quarks give the particle its main identity, but they are not the whole interior. Between and around them are gluons, the carriers of the strong force. Gluons bind quarks the way no ordinary glue binds ordinary objects. They are excitations of the strong field, constantly exchanged, emitted, absorbed, and reworked in the tiny volume of the neutron. The field is not quiet. It is active even when the particle appears calm. The neutron's interior contains what physicists often call a quark and gluon sea. This phrase points to a restless background where gluons carry energy, and where pairs of quarks and antiquarks appear for tiny intervals before vanishing again. These are not permanent residents in the same way as the three valence quarks, but their presence affects the particle. The neutron is made of three defining quarks, plus a moving field of strong interaction around them. Even the neutron's neutrality has texture. Experiments show that the positive and negative charges inside it are not spread evenly in a simple, featureless way. They have a distribution. The total remains zero, but zero is the final sum of an internal arrangement. The outside says neutral. The inside says charged motion. This helps explain another old clue. The neutron has no electric charge, yet it has a magnetic moment. A magnetic moment is a measure of how a particle responds to a magnetic field, as though it contains a tiny source of magnetic behavior. A truly featureless neutral particle would not be expected to have one. The neutron does. Its charged quarks, moving within the bound system, give rise to that magnetic property. A neutron really is neutral. It really does sit in the nucleus. It really does help stabilize many atoms. None of those statements are false. They are simply not the whole story. Beneath them is a different layer, where the neutrality comes from cancellation, where the mass comes mostly from energy, and where stillness is only the outward face of confined motion. The smallness of this world is almost impossible to picture. A neutron is about a femtometer across, and a femtometer is 1/quadrillionth of a meter. The number is less useful than the feeling of it. An atom is already far too small for direct human experience, yet the nucleus is thousands of times smaller than the atom, and the neutron is one of the pieces inside that nucleus. Within that hidden point, the quarks are trapped. Quarks have never been observed as isolated free particles. Whenever energy is used to pull them apart, the strong field responds in a way that creates new quark combinations instead of releasing a single quark into the open. The result is always a color-neutral particle, never a lone-colored quark. Nature seems to allow the quark to show its effects, but not its solitude. This mirrors the neutron's larger story in a smaller form. The quarks inside a neutron cannot be alone. The neutron outside a nucleus cannot last. At one scale, color confinement keeps quarks bound into particles. At another, nuclear binding can shelter neutrons inside atoms. Matter is layered with forms of dependence. The deeper the path goes, the less it looks like a universe of separate little things, and the more it looks like a universe of relationships held in balance. From the outside, all this is hidden. A neutron passing through a detector, or sitting inside carbon, or buried in the iron nucleus of a blood cell, does not show its inner weather to ordinary sight. It behaves as one particle, with one mass, one spin, one neutral charge, one identity. Physics often works this way. An object presents a simple face, because many deeper motions have settled into a stable pattern. That stable pattern is not permanent in every setting. The quarks remain bound by the strong force. The neutron remains itself for as long as its inner arrangement stays unchanged, but one of its down quarks has a path, rare and slow by particle standards, through which it can become an up quark. The strong force cannot make that transformation. It holds the quarks together, but it does not change their flavor. The force that can do that is quieter, shorter ranged, and far weaker. The neutral shell has now given way to the charged pieces beneath it. Those pieces are held in a field that refuses to let them go. Yet hidden inside the same particle is the possibility of change, waiting for the weak force to act. Before that transformation can be understood, the force that binds the quarks must be followed more closely, because the neutron's calm depends first on the strength of its cage. The strong force is poorly named for how little of it reaches ordinary life. It is the strongest of the known forces, yet it stays hidden inside the smallest chambers of matter. It does not pull planets into orbits. It does not carry light across space. It does not make a compass turn, or a dropped object fall, or static electricity lift a strand of hair. It does its work almost entirely inside atomic nuclei, and deeper still, inside the proton and the neutron. In that narrow domain, it dominates everything. The quarks inside a neutron are not merely near each other, they are confined. Their freedom is not like the freedom of planets moving around a star, where a body might be flung away if enough speed is given to it. A quark cannot be taken from the neutron and placed alone in space. The attempt changes the system before isolation can happen. The more energy used to pull a quark away, the more energy gathers in the strong field between the quarks, until that energy forms new quarks and antiquarks. Instead of one escaped quark, there are new bound particles. The cage repairs itself by becoming more matter. This rule is called confinement. It is one of the reasons the inner world of the neutron feels so different from ordinary intuition. With gravity, distance weakens the pull. With electromagnetism, distance also weakens the force between charges. Two magnets moved apart lose their grip on each other. Two charged particles separated farther and farther feel less and less. The strong force does not behave that way at the scale where quarks are being pulled apart. Its field stretches like a tight tube, and the stored energy grows until separation is no longer the right description. Creation takes over. The word color is used for the strong charge that quarks carry, but it is only a label. No quark is red in the visual sense. No green or blue light glows inside the neutron. Physicists borrowed the language because it gave a simple way to describe a threefold kind of charge. A proton or neutron is color neutral when its three quarks combine their strong charges into a balanced whole. The comparison with red, green, and blue light making white is helpful only as a doorway. Past the doorway, the physics is stranger. Each quark carries color charge. Gluons carry the force between those charges. Unlike photons, which carry electromagnetism but do not carry electric charge themselves, gluons carry color charge. This means they interact not only with quarks, but with each other. The carriers of the force also feel the force. A gluon can emit another gluon. A gluon can absorb another gluon. The field becomes tangled with itself. That self-interaction gives the strong force its sealed, inward character. The force is not a simple thread tied from one quark to another. It is a dense, changing field, alive with exchanges too brief and too small for direct sight. Inside a neutron, gluons are constantly being traded among the quarks. They do not form a static glue, they form motion, they form tension. They form the conditions under which the neutron exists as one particle. The three valence quarks define the neutron, two down quarks and one up quark, but the strong field around them is not empty space. Gluon energy can briefly produce quark and antiquark pairs, which appear and vanish as part of the quantum field's allowed fluctuations. These pairs are not permanent in the same way as the valence quarks. They are more like small waves rising and falling on a dark surface. Yet they matter. They help shape the particle's mass, its internal charge distribution, and the way it responds when struck by other particles. The neutron is therefore not three objects sitting quietly in a room. It is a confined storm whose average behavior looks like a single neutral particle. This matters because the neutron's stability begins with that confinement. The strong force does not allow the quarks to drift away from each other. It holds the neutron's inner pattern together so completely that the particle can cross a detector, sit in a nucleus, or pass through certain forms of matter as one recognizable object. The neutron has a definite mass. It has spin. It has a magnetic moment. It has no net electric charge. Those outward traits are the calm surface of the deeper field. The power of the strong force is difficult to compare with familiar things, because familiar things are built from the strong force already doing its hidden work. Still, the contrast helps. Electromagnetism shapes atoms and chemistry. Gravity shapes planets, moons, stars, and galaxies. The strong force is far more powerful at its own scale, yet its reach is so short that it almost never escapes the nucleus. Its strength is immense, but its territory is tiny. A force can rule a kingdom too small to see. The range of the force between quarks is bound up with confinement, and the residual nuclear force between protons and neutrons reaches only across distances comparable to the size of a nucleus. Beyond that, the strong interaction is effectively silent. A person can stand on a planet because gravity acts over planetary distances. Light can cross a room because electromagnetism can travel outward as photons. But the strong force is locked into the heart of matter. It does not announce itself, except through the existence of the matter it holds together. In the neutron, this force has to do more than overcome electric charge. The quarks are light, and because they are confined to such a small region, quantum mechanics forces them into intense motion. The uncertainty principle says that a particle whose position is tightly limited cannot also have a sharply defined, gentle momentum. In practice, the quarks inside the neutron move at speeds close to light, not because they are little planets racing around a center, but because quantum confinement demands restless motion. The neutron is quiet only from far away. Its interior is a place where the idea of a solid object begins to break down. There is no hard shell in the ordinary sense. There are no fixed edges like the surface of a grain of dust. There is a region in which the fields and particles that make the neutron are concentrated, and beyond which the neutron's identity fades into interaction with the rest of the world. The boundary is real enough for experiments to measure size, scattering, and structure, but it is not a wall. The same is true of the quarks. They are not tiny colored marbles with polished surfaces. They are excitations of quantum fields, carrying charges that determine how they interact. Their individuality matters, but it cannot be separated from the field binding them. A down quark inside a neutron is part of a larger pattern. So is the other down quark. So is the up quark. None of them can be lifted out and kept as a specimen. This is why particle collisions do not produce free quarks. When high-energy particles strike protons or neutrons, the quarks inside can be disturbed violently. Energy pours into the strong field. Out of the collision come jets of particles, narrow sprays of hadrons, such as pions, kaons, protons, and other composite states. Those jets are not escaped quarks. They are the trace, left by confinement under stress. The quark tries, in a sense, to separate, and the field answers by making more color-neutral particles. Only the aftermath is visible. In a deep space documentary about stars and galaxies, this may seem at first like a journey too far inward, yet the connection is direct. Every star holds itself together with gravity, but the matter inside the star exists because the strong force has already built protons and neutrons. Every planet is made of atoms, and most of the mass of those atoms lies in nuclei. Every heavy element forged in stellar death depends on the same hidden binding. The strong force is not a distant subject from astronomy. It is the reason astronomical bodies have substance at all. When a massive star later collapses, this hidden force meets gravity under conditions far beyond ordinary matter. When a neutron star forms, the story of neutrons is no longer confined to a single particle in a nucleus. It becomes the story of an entire stellar remnant, where matter is pressed so tightly that nuclei, electrons, and free neutrons enter states unlike anything on Earth. But before that large ending can be reached, the small interior still has one more secret to offer. The strong force gives the neutron its bound form. It holds the quarks in a state that cannot be undone by simple separation. It stores enormous energy inside a space far smaller than an atom, and that stored energy leads to a quiet surprise. The neutron's mass, the weight it contributes to the world, does not mostly come from the tiny bare masses of its quarks. It comes from the motion, tension, and energy of the strong field itself. The cage is heavy because the cage is alive. Mass seems like one of the simplest things in the world. A stone has weight in the hand. Water presses downward in a glass. A planet holds an atmosphere because its gravity comes from mass, and a star bends the paths of smaller bodies because its mass gathers space around it. Matter feels substantial. It feels as if substance must come from tiny solid ingredients stacked together, each one adding its own small heaviness to the whole. At the scale of the neutron, that simple feeling begins to fail. The neutron is made from 3 valence quarks, 2 down quarks and 1 up quark. But the bare masses of those quarks are only a small part of the neutron's total mass. If those quark masses are added together, the result is far too light. It accounts for only a narrow fraction of what the neutron weighs. The rest is not hidden in some heavier, unseen bead. It comes from energy, from the confined motion of the quarks, from the gluon field that binds them, and from the constant quantum activity inside the particle. This is where matter becomes less like a pile of pieces and more like a held condition. The neutron has mass because its interior is not still. The quarks are confined in a space so small that their motion is forced into the relativistic world, where speeds near light and energies of fields cannot be ignored. Gluons fill the system with interaction. Virtual quark and anti-quark pairs rise and disappear. The strong field stores tension. All of that energy contributes to the mass of the neutron. Einstein's relation between energy and mass is often written as a famous equation, but inside the neutron it is not a slogan. It is the daily accounting of matter. Energy confined inside a particle appears as mass. The neutron's weight is mostly the weight of motion and binding, not the quiet weight of the quarks themselves. A person touching a table does not feel this directly. The table seems hard because atoms resist compression through electromagnetic interactions between their electrons. But the mass of the atomic nuclei inside that table, the mass that gives the table its heaviness, is mostly tied to the energy of the strong force inside protons and neutrons. The same is true for stone, metal, bone, and the iron buried in the cores of planets. The visible world is heavy because tiny regions of field energy are locked into stable particles. The quarks do have their own masses. They are not massless. Their small, intrinsic masses come from their interaction with the Higgs field, a field present throughout space. When particles interact with that field, they acquire rest mass. The discovery of the Higgs boson confirmed that this mechanism is part of the structure of the known universe. But in ordinary matter, this contribution is only a beginning. For protons and neutrons, the Higgs field gives the quarks a small seat of mass, while the strong force supplies almost everything that is felt as nuclear mass. This distinction matters. It means the mass of familiar matter is not simply placed into the universe as a fixed property of tiny building blocks. Much of it is generated by relationship, confinement, and energy. The quarks have mass, but the neutron has far more mass than the quarks alone can explain. The system weighs more because the system is active. There is a quiet beauty in that. The neutron appears as a single neutral particle, yet its mass is the result of a hidden storm that never rests. Its quarks cannot sit still because quantum confinement gives them no room for stillness. Its gluons cannot form a frozen lattice because the strong force is a living field of exchange. The particle remains stable in form, but not because its interior is calm. It remains stable because the activity inside it is balanced. Balance is not the same as silence. The same principle carries outward. A proton receives most of its mass in the same way. Atomic nuclei inherit their mass from protons and neutrons, while molecules inherit mass from their atoms. Rocks, oceans, atmospheres, and planets inherit mass from the particles beneath them. By the time matter appears on a scale large enough to touch or see, hidden field energy has become the simple experience of weight. That translation is easy to forget. The hand does not feel gluons. A falling stone does not reveal color confinement. A mountain does not seem like a vast collection of strong fields locked into nuclear matter. Yet that is what the mountain is. Its mass is not mostly the sum of solid little grains at the deepest level. It is energy held in patterns that have persisted across cosmic time. Inside stars, this fact becomes part of a larger balance. Gravity pulls stellar matter inward because mass curves space-time. Pressure pushes outward because hot particles move and collide. The mass doing the gravitational work is the same mass generated mostly by strong force energy inside nuclei. Stars are therefore not only balls of hydrogen and helium in the chemical sense. They are structures built from particles whose mass is already a result of confined field energy. The star's gravity begins with the hidden energy of its smallest stable pieces. The neutron is one of those pieces, but it carries a small asymmetry that will matter later. It is slightly heavier than the proton. The difference is tiny compared with the total mass of either particle, yet it changes the fate of the free neutron. If the neutron and proton had exactly the same mass, or if the proton were heavier in just the wrong way, the chemistry of the universe would not be the same. Ordinary hydrogen depends on proton stability. The formation of helium in the early universe depends on neutrons surviving long enough to be captured. Small mass differences become cosmic boundaries. The source of that neutron-proton difference is delicate. The neutron contains 2 down quarks and 1 up quark. The proton contains 2 up quarks and 1 down quark. Down quarks are a little heavier than up quarks, which tends to make the neutron heavier. Electromagnetic energy works in the other direction, because the proton's positive charge creates its own internal energy cost. The final balance leaves the neutron heavier by a small amount. Not much. Just enough. Just enough for decay. This small excess mass is what a free neutron can release when it becomes a proton, an electron, and an electron antineutrino. The energy does not pour out like fire. It is divided among the products of decay as motion. The proton recoils gently. The electron leaves with a range of possible energies. The antineutrino carries away energy and momentum almost without touching anything else. The whole event is modest in scale, but it changes the identity of the particle completely. The same mass difference also sits quietly inside stable nuclei, waiting without effect when the energy landscape does not permit decay. A neutron inside carbon-12 remains protected because becoming a proton would create a final nuclear state with too much energy. A neutron outside the nucleus has no such shelter. Its extra mass becomes available. The weak force provides the path. The particle changes. Before following that weak path in detail, it helps to stay with what has been revealed. The neutron's mass is not the simple mass of its pieces. Its neutrality is not the absence of charge. Its stillness is not internal rest. Again and again, the outward trait is an average, a balance, a final appearance created by deeper motion. This is a recurring pattern in physics. The world seen at one scale can be real and incomplete at the same time. A still lake may hide currents. A quiet night sky may contain stars forming behind dark dust. A stable atom may contain particles moving according to rules no ordinary image can hold. The neutron belongs to that kind of reality. It is simple enough to be counted in a nucleus, but not simple enough to be understood as a bead of matter. It is a held storm with a number attached to it, mass. And because that mass is slightly larger than the mass of a proton, the neutron carries within it a possible future. Not a future caused by the strong force. The strong force holds the quarks together and gives the neutron most of its weight, but it does not turn one quark into another. The coming transformation belongs to a different force, weaker in strength, shorter in reach, and slower in action. It does not bind the neutron. It changes what the neutron is allowed to become. The strong force has made the cage heavy. The weak force will open a hidden door. The weak force does not announce itself with strength. It does not build the neutron's mass. It does not confine quarks. It does not hold the nucleus together against the electric repulsion of protons. Compared with the strong force, it is faint, short-ranged, and slow. Yet it carries a power that the strong force does not have. It can change identity. Inside a neutron, the strong force keeps the three valence quarks bound in their restless pattern. Two down quarks and one up quark remain together, wrapped in the gluon field, held so tightly that none of them can be isolated. The strong force keeps the system intact, but it cannot decide whether a down quark remains down forever. It does not change quark flavor. It binds what is there. The weak force is different. It can reach into the structure of a particle and allow one kind of quark to become another kind. That is its strange gift. It is not powerful in the way a cage is powerful. It is more like a hidden rule in the bookkeeping of nature, a permission that exists only when the energies, charges, and quantum states can all be made to balance. For a free neutron, that permission is enough. The neutron is slightly heavier than the proton. The difference is small, less than the mass of two electrons. But in the quiet accounting of particles, small differences matter. A free neutron has a lower energy path available to it. It can become a proton, and the remaining energy can be carried away by lighter particles. The decay does not happen because the neutron cracks open. It happens because one quark inside it changes. One of the two down quarks becomes an up quark. Before the change, the neutron has two down quarks and one up quark. After the change, it has two up quarks and one down quark. That new arrangement is a proton. The particle has crossed from neutrality into positive charge, not by gaining something from outside, but by rearranging the identity of one of its inner pieces. The change cannot happen carelessly. Electric charge must be conserved. A down quark carries a negative charge of 1/3. An up quark carries a positive charge of 2/3. The transformation increases the quark's charge by 1 full unit. That extra positive charge cannot appear without balance. Nature keeps the ledger clean. So the changing quark emits a W- boson. The W- boson is one of the carriers of the weak force. It carries 1 unit of negative charge, exactly balancing the increase in the quark's charge. The down quark becomes an up quark, and the W- carries away the missing negative charge. For an unimaginably brief interval, the transformation has a messenger. Then the messenger itself decays. The W- boson is far too heavy to exist as an ordinary long-lived particle in this process. A neutron does not contain enough available mass energy to produce a real W boson that can travel away freely. The weak interaction uses a virtual W boson, a temporary quantum presence that appears only within the limits allowed by uncertainty. It is not a particle that can be caught leaving the neutron like an electron leaving a radioactive nucleus. It is the short-lived internal bridge through which the change occurs. The W- then becomes an electron and an electron antineutrino. The electron carries the negative charge. The antineutrino carries no electric charge, but it takes away energy and momentum, slipping out with almost no interaction with the surrounding world. The final state is simple to name: a proton, an electron, and an electron antineutrino. The neutron is gone. This is beta minus decay. The name is old, inherited from the first studies of radioactivity, when emissions from unstable nuclei were sorted into alpha, beta, and gamma radiation, before their inner causes were known. Beta radiation turned out to include electrons or their antimatter partners. In the case of a free neutron, beta minus decay is the path by which a neutral baryon becomes a positive baryon and sends out a negative electron. The event is small, but it is not incomplete. Every conservation law is obeyed. Charge is conserved. Energy is conserved. Momentum is conserved. Angular momentum is conserved. The electron and antineutrino share the available energy in different amounts from one decay to another, which is why emitted electrons do not all carry the same energy. That variation once looked like a problem so serious that it threatened the conservation of energy itself. The antineutrino solved the problem. It is one of the quietest particles in the story. It has almost no mass, or at least a mass so small that it remains difficult to measure directly. It has no electric charge. It does not feel the strong force. It interacts through the weak force and gravity is almost nothing for something so light. Most antineutrinos pass through ordinary matter as if the matter were not there. Stone, metal, water, air, and flesh are nearly transparent to them. When the neutron decays, the antineutrino leaves without ceremony. It carries its share of the energy away into space, through the walls of laboratories, through planets, through the dark between stars. A particle born in one quiet decay may travel for enormous distances before any interaction marks its passage. Most will never be noticed. The electron is less ghostly. It carries charge and can interact readily with matter. In nuclear beta decay, streams of such electrons were what early physicists could detect. The proton remains behind as the heavier charged remnant, the particle that the neutron has become. If the decay occurs in empty space, the proton and electron separate. If it occurs in a nuclear environment, the result can change the identity of an atom, turning one element into another. That is the reach of the weak force. It can alter the chemical future of matter by changing the balance of protons and neutrons in a nucleus. A neutron-rich nucleus can move toward stability when one of its neutrons becomes a proton. A proton-rich nucleus can sometimes move the other way through a related weak process that turns a proton into a neutron. The weak force is not loud, but it gives matter a way to adjust itself when the energy landscape allows transformation. The slowness of the weak force is just as important as its ability. In the world of particle physics, a free neutron lasting minutes is astonishingly long. Strong interactions unfold over intervals so brief that ordinary time comparisons become useless. Electromagnetic interactions are also fast. The weak force can wait. It can leave a neutron, apparently unchanged, through millions upon millions of internal strong force exchanges before one rare, weak event finally occurs. That slowness gives the neutron its strange, middle nature. It is not stable in isolation, but it is not instantly destroyed. It has time. In the early universe, those minutes mattered. A neutron could survive long enough to be captured into the first helium nuclei, if the expanding universe cooled quickly enough. Inside stars, weak interactions are slow enough to regulate fusion, making stellar lives long and steady. A force that seems feeble by comparison with the strong force becomes one of the reasons cosmic change can unfold gently over vast ages. The weak force also carries a kind of restraint. It does not transform every possible particle at every moment. The process must be allowed by energy, charge, and quantum state. A free neutron has a path downward into a proton. A free proton does not have a path upward into a neutron, because that would require extra energy. Inside a nucleus, either direction can become possible or impossible depending on binding energy and the arrangement of nucleons. The weak force opens doors only where the floor slopes the right way. For the free neutron, the floor slopes toward decay. The strong force continues holding the quarks together during the transformation. It does not fail. The neutron does not dissolve into loose quarks. Instead, the quark pattern changes from one allowed bound state into another. The strong force then binds the new set of quarks as a proton. The weak force changes the identity. The strong force preserves the form of a baryon around that change. The handoff is exact and silent. This is why the death of a neutron is not simple destruction. It is conversion. The material does not vanish. The energy does not vanish. The charges do not break the rules. A neutron becomes a proton, an electron, and an antineutrino, because the structure of the universe permits that arrangement to hold less energy than the one before it. Decay is not chaos. It is order moving downhill. And yet, the same weak mechanism will not always succeed. A neutron inside a stable nucleus may contain the same quarks, the same possible weak transformation, the same hidden path from down quark to up quark, but the surroundings change the accounting. The proton that would be created may not have an available low-energy place to go. The new nucleus may weigh more, not less. The decay may require energy instead of releasing it. The weak force is still there. The door is still part of nature. But a door that opens uphill does not open by itself. The next part of the story lies in that difference. The neutron has been seen alone, where its extra mass can become motion and its quark pattern can shift into a proton. Now the same particle has to be placed back into the dense center of the atom, among other protons and neutrons, where the strong force creates binding energy and the landscape of decay changes completely. There, the neutron may stop being mortal, not because it has changed, but because it has found the right place to remain. The free neutron lives long enough to become familiar and not long enough to become simple. In particle physics, a lifetime measured in minutes is almost slow beyond belief. Many unstable particles vanish before light can cross the width of an atom. Some live for less than the briefest fraction of a second, appearing only as traces in collision debris. The neutron, by contrast, can be stored, guided, counted, and watched. It gives experimenters time to prepare a trap, open a shutter, measure a beam, and ask the same question again. How long does it really live? The answer sounds easy at first. A free neutron has a mean lifetime of a little under 15 minutes and a half-life of about 10 minutes. Those values are close enough for explaining why free neutrons decay, why the early universe had only a limited time to make helium, and why isolated neutrons do not fill the space between stars. But precision has a way of turning approximate answers into quiet mysteries. When physicists try to measure the neutron lifetime with great care, two different methods have not always agreed. The disagreement is small in human terms. It is not minutes. It is only several seconds. Yet for the neutron, several seconds matter. For the early universe, several seconds can affect the predicted abundance of light elements. For particle physics, a persistent difference between careful experiments is not something to ignore. It may be an unnoticed error. It may be an experimental difficulty not yet fully understood. Or, less likely but more tempting, it may be a sign that the neutron still has a path hidden from the standard picture. The first way to measure the lifetime is often called the beam method. In this approach, a stream of cold neutrons travels through an apparatus. The experimenters know, as precisely as possible, how many neutrons pass through a defined region. Some of those neutrons decay while moving through that region. When they decay, they produce protons, electrons, and electron antineutrinos. The antineutrinos are far too ghostly to catch in such an experiment, but the protons or electrons can be counted. By comparing the number of neutrons in the beam with the number of decay products detected, the lifetime can be inferred. The idea is clean. A known number of neutrons enters. A certain number decay. The rate of decay reveals the lifetime, but cleanliness in concept does not mean simplicity in practice. Neutrons have to be counted without disturbing them too much. Decay protons have to be collected efficiently. The geometry of the beam, the strength of magnetic and electric fields, the behavior of detectors, and the background from other particles all have to be understood. Every small correction matters. A tiny loss, a tiny miscount, a tiny unrecognized bias can become a few seconds in the final result. The second approach is called the bottle method. Instead of watching neutrons pass through a beam, physicists store ultra-cold neutrons in a trap. These neutrons move slowly enough that they can be held by material walls, magnetic fields, gravity, or some combination of these. The trap is filled, time passes. Then the remaining neutrons are counted. If fewer neutrons are left after a known interval, the loss gives the lifetime. This method also sounds simple. Put neutrons in a bottle, wait, count what remains. The difficulty lies in the word loss. A neutron can disappear from the trap because it decays, but it can also be lost for other reasons. It might strike a wall and be absorbed. It might gain enough energy to escape. It might find a tiny imperfection in the storage environment. Early bottle experiments had to struggle with the fact that the walls themselves could remove neutrons in ways that had nothing to do with beta decay. Modern magnetic and gravitational traps reduce those problems, but every experiment still has to prove that what is being counted is decay, not leakage. For years, beam measurements and bottle measurements have tended to point to lifetimes that differ by a small but stubborn amount. Bottle experiments generally find a shorter neutron lifetime. Beam experiments generally find a longer one. The gap is not large enough to rewrite physics by itself, but it has lasted long enough to become known as the neutron lifetime puzzle. There is a certain stillness in that phrase. It is not a puzzle of distant galaxies or dark matter across the cosmic web. It belongs to one of the most studied particles in ordinary matter. It concerns a particle found in every stable nucleus, heavier than common hydrogen. It is not hidden in the darkness between stars. It is hidden in measurement, in the difference between watching neutrons decay and watching them remain. One possible answer is ordinary and difficult. One or both experimental methods may contain systematic effects not fully understood. A systematic effect is not random noise. It is a small, consistent bias in the way a measurement is made. Random errors can be reduced by collecting more data. Systematic errors must be found, named, and removed. They live in detector efficiency, background subtraction, field shape, neutron spectrum, wall losses, calibration, and the quiet assumptions built into an apparatus. Physics often advances by discovering that an instrument has been whispering into the result. Another possibility is more speculative. Some have wondered whether a neutron might sometimes decay through channels that are hard for beam experiments to see. If a neutron decayed into particles that did not produce the expected proton, a beam experiment counting protons could miss that decay, making the neutron appear to live longer. Bottle experiments, which count how many neutrons remain, would still see the neutron disappear. This kind of idea has led to proposals involving dark decay modes or hidden sector particles. Most such possibilities are tightly constrained by other observations and experiments. They are not accepted explanations, but they show why the discrepancy has attracted attention beyond the measurement itself. The honest position is quieter. The neutron lifetime is still being measured. Better traps, colder neutrons, improved detectors, and refined analysis continue to press on the discrepancy. Some results narrow the allowed values. Some improve one method more than another. The puzzle may eventually dissolve into a well-understood experimental correction. Many puzzles in physics do. A loose edge in the apparatus is found. A background is removed. A calibration changes. The mystery becomes a lesson in care. Or it may not. That uncertainty should not be exaggerated, but it should not be hidden. A few seconds in the life of a neutron may seem almost nothing beside the age of stars. But the early universe was once young enough for seconds to matter. Big Bang nucleosynthesis, the formation of the first light nuclei, depends on how many neutrons survive before they are locked into helium. Change the neutron lifetime slightly, and the predicted abundance of helium shifts slightly. Observations of primordial elements then become part of the same quiet conversation as laboratory traps on Earth. This is one of the strange bridges in physics. A chamber built in a laboratory, cooled and shielded, and watched by instruments, connects to the first minutes after the Big Bang. A neutron stored in a bottle speaks, indirectly, about the chemical beginning of the cosmos. The question of how fast a single particle decays becomes part of the question of why the universe contains the amount of helium it does. The bridge also runs inward. The neutron lifetime tests the weak force. It tests the parameters used to describe how quarks change flavor. It tests the consistency of the standard model in one of its most delicate low-energy processes. The event itself is modest. A down quark becomes an up quark. An electron and antineutrino leave. A proton remains. But measuring how often that happens requires every piece of the theory and every piece of the experiment to line up. The neutron, then, is not only a decaying particle. It is a clock, not a clock with gears or hands, but a statistical clock, one that ticks through probability. No single neutron carries a visible countdown. One may decay quickly, another may last longer. A large collection reveals the rhythm. The lifetime is the shape of that rhythm when many individual uncertainties are gathered into one number. A few seconds of disagreement means the rhythm has not been heard with complete clarity. There is something fitting about that. The neutron has already resisted simple pictures. It is neutral but full of charge. It is massive but mostly from energy. It appears calm but contains a sea of gluons. It is stable in one setting and unstable in another. Even its free lifetime, which might seem like a finished fact, still carries a small, unresolved shadow. That shadow is useful. It keeps the story from becoming too polished. Nature is not required to match the first clean explanation offered for it. Measurements have to be repeated. Apparatus has to be rebuilt. Old assumptions have to be tested against colder neutrons, cleaner traps, sharper beams, quieter backgrounds. The neutron remains there in the center of the work, ordinary enough to be everywhere, strange enough to resist being fully closed, and while the laboratory continues to ask how long the free neutron truly lives, the larger answer remains clear enough for the path ahead. Alone, the neutron is not safe. Its lifetime is short on cosmic scales, whether the exact number lands on one side of the puzzle or the other. Inside the right nucleus, the same neutron may endure across the age of a planet. The next step is to return it to that shelter and see why the clock can stop. A neutron outside a nucleus has a path open beneath it. Its mass is slightly larger than the mass of the proton it can become, and the weak force provides the transformation. The decay is allowed. The energy can be balanced. The products can exist. In empty space, there is nothing around the neutron to change that accounting, so the particle follows the slope that nature gives it. Inside a stable nucleus, the same neutron enters a different landscape. It still has 2 down quarks and 1 up quark. The weak force still exists. The possible transformation from down quark to up quark has not been erased from the laws of physics. Nothing inside the neutron has become magically immune to decay. The difference is not in the neutron alone. It is in the system that holds it. A nucleus is not just a container. It is a bound state, a shared arrangement of protons and neutrons whose total energy is lower than the energy those particles would have if they were separated. When nucleons come together under the nuclear force, energy is released. The bound nucleus weighs slightly less than its free pieces would weigh apart. That missing mass has not disappeared. It has left as binding energy, the energy that would have to be supplied again to pull the nucleus apart. This is the first step toward understanding why a neutron can survive there. A bound neutron is not resting in the same energy condition as a free neutron. It has been lowered into a well made by nuclear binding. To change into a proton, it would not only have to perform the weak transformation inside itself, the entire nucleus would have to be able to rearrange into a new state with the extra proton in place. If that new state has lower total energy, decay can occur. If it has higher total energy, decay cannot happen spontaneously. The neutron may contain the door, but the room beyond it must be lower. In free space, the room beyond is lower. A neutron becomes a proton, an electron, and an antineutrino, with energy left over as motion. Inside carbon-12, oxygen-16, helium-4, or iron-56, the situation can be reversed. A neutron, changing into a proton, would alter the balance of the whole nucleus. It would increase the number of protons, increase the electric repulsion among them, and force the new proton to fit into the quantum structure already occupied by other protons. The final arrangement may cost more energy than the decay can provide. Then the neutron remains. This is binding energy as shelter. It is not a wall blocking the weak force. It is not a shield wrapped around the neutron in a mechanical sense. The weak force is still present, still permitted by the deep rules of particles. But the final state is not available. The decay would need energy from outside, rather than releasing energy outward. A system does not roll uphill by itself. The image of a valley helps, as long as it is kept gentle. A free neutron sits on a slope that leads downward to the proton state. A bound neutron can sit in a valley where the same proton state lies higher, once the whole nucleus is counted. The slope has been reshaped by other nucleons, by nuclear attraction, by electric repulsion, and by the exclusion rules that govern identical particles. The particle is the same, the ground beneath it is not. The nuclear force that creates this shelter is related to the strong force, but it appears at a larger scale. Inside each proton and neutron, quarks are held by gluons. Between neighboring protons and neutrons in a nucleus, there is a residual form of the strong interaction. The nucleons are color neutral overall, so the raw color force does not simply pour outward without limit. Yet a short-ranged attraction remains, strong enough to bind nearby nucleons together. This nuclear force acts only across very small distances, roughly the span of a few nucleons. Each proton or neutron mainly feels its closest neighbors. The force is attractive at the right separation, but at very short range it becomes repulsive, preventing the nucleus from collapsing into a point. That balance gives nuclei their size. It lets the center of the atom be dense, without becoming formless. Protons add a complication. They carry positive electric charge, and like charges, repel. In a small nucleus, the nuclear force can overcome that repulsion without much difficulty. In helium-4, 2 protons and 2 neutrons form a tightly bound system. In carbon-12, 6 protons and 6 neutrons sit in a deeper arrangement of stability. But as nuclei grow heavier, more protons mean more electric repulsion. Unlike the nuclear force, electromagnetism reaches across the whole nucleus. Every proton repels every other proton, even if they are not close neighbors. Neutrons help solve that problem. They contribute to the attractive nuclear force without adding electric repulsion. In heavier nuclei, extra neutrons act as a kind of silent support. They deepen the binding and spread the nuclear structure without increasing the positive charge. That is why stable heavy nuclei usually contain more neutrons than protons. Iron has more neutrons than protons. Lead has many more. The heavier the nucleus becomes, the more the balance leans toward neutron richness. But there is no unlimited safety in simply adding neutrons. Neutrons, like protons, are fermions, particles that cannot all occupy the same quantum state. As more neutrons are added, higher neutron states must be filled. Too many neutrons can raise the energy of the system until a neutron decay becomes favorable again. Then beta-minus decay occurs inside the nucleus. A neutron becomes a proton, an electron, and an antineutrino, and the nucleus moves closer to balance. Carbon-14 carries this principle quietly. It has 6 protons and 8 neutrons. The stable form of carbon has 6 protons and 6 neutrons. With 2 extra neutrons, carbon-14 sits outside the deepest part of stability. One of its neutrons can decay into a proton, turning the nucleus into nitrogen-14. The process is slow on human scales, with a half-life of thousands of years, but it follows the same rule as the free neutron. The energy landscape allows the transformation, so the weak force can act. Carbon-12 does not offer that path. Its 6 protons and 6 neutrons form a stable arrangement. A neutron inside it cannot simply become a proton without pushing the nucleus into a higher energy state. The weak process is not energetically allowed. The neutron remains a neutron, not because the weak force is absent, but because there is no lower place for the system to go. This is the valley of stability in miniature. Across the chart of nuclei, each isotope has its own balance of proton number and neutron number. Some sit near the bottom of the valley, where no easy decay path leads downward. Others lie to one side with too many neutrons, and they tend to move inward through beta- decay. Others lie on the opposite side with too many protons, and they may move inward through beta plus decay or electron capture. The weak force becomes the quiet mechanism by which nuclei adjust their identity. The stable nucleus is not frozen because nothing is happening inside it. Nucleons still move. Fields still fluctuate. The quantum system still has structure. Stability means something more precise and more subtle. No allowed lower energy state is available through the processes under consideration. The forces remain. The possibilities remain in the laws. The transition simply cannot pay for itself. This idea reaches far beyond the neutron. A chemical molecule is stable if breaking or rearranging it would require energy rather than release it. A star remains on the main sequence while pressure and gravity hold a working balance. A rock rests at the bottom of a hollow because gravity offers no lower nearby place. Stability is not the absence of forces. It is the shape of the landscape. For the neutron, that landscape decides everything. Removed from the nucleus, it is exposed to its slight excess mass and the weak path toward the proton. Bound inside the right nucleus, it is lowered into a shared state where the same transformation would cost too much. The neutron does not become a different kind of particle. It becomes part of a different whole. That is why some neutrons in ordinary matter are ancient. The neutrons in stable oxygen, carbon, calcium, and iron do not carry little countdown clocks of 10 minutes. Their fate is bound to the fate of the nuclei holding them. Unless those nuclei are broken by some outside process, the neutrons remain. They can pass through the life of a star, the formation of a planet, the long cooling of stone, and the brief warmth of a living body without decaying. A free neutron is mortal. A bound neutron may be almost timeless. The contrast is not poetic decoration. It is physics. The same weak force, the same quark transformation, the same neutron-proton mass difference, and yet two outcomes divided by context. The nucleus gives the neutron a home by changing what decay would mean. It does not silence the laws of nature. It arranges them into safety. Across the chart of nuclei, stability forms a narrow path. It is not a straight line, and it is not centered on equal numbers of protons and neutrons for very long. Near the lightest elements, the balance looks simple. Helium-4 has 2 protons and 2 neutrons. Carbon-12 has 6 and 6. Oxygen-16 has 8 and 8. In these small nuclei, the pull of the nuclear force is strong enough, and the electric repulsion among protons is still modest enough that equal numbers can sit near the bottom of the energy landscape. Then the path bends. As nuclei grow heavier, protons become more costly. Every proton carries positive charge, and every other proton feels that charge. The nuclear force reaches only to close neighbors, but electric repulsion reaches across the whole nucleus. A proton near one side of a large nucleus still repels a proton on the other side. The attraction is local. The repulsion accumulates. For a large nucleus to survive, something has to deepen the binding without adding more positive charge. Neutrons do that work. They are not passive filler. They add to the attractive nuclear force. They occupy quantum states. They help spread and stabilize the nucleus. A neutron brings mass and strong interaction without electric repulsion. In the heavier elements, this makes neutrons essential. Iron-56 has 26 protons and 30 neutrons. Tin-120 has 50 protons and 70 neutrons. Lead-208, one of the heaviest stable nuclei, has 82 protons and 126 neutrons. The heavier the nucleus, the more neutron-rich stability becomes. This is sometimes described as the Valley of Stability. On a chart with proton number rising in one direction and neutron number rising in another, the stable nuclei lie along a curved valley floor. Nuclei with too many neutrons sit on one slope. Nuclei with too many protons sit on the other. The unstable ones tend to move downhill toward the valley, not by rolling through space, but by changing identity through nuclear decay. A neutron-rich nucleus can lower its energy by turning one neutron into a proton, that is beta-minus decay. A down quark becomes an up quark. An electron and an electron antineutrino are emitted. The atomic number rises by 1. Because the nucleus now has one more proton, the element changes. A proton-rich nucleus can move in the opposite direction. Through beta plus decay or electron capture, a proton becomes a neutron, and the atomic number falls by 1. In both cases, the weak force adjusts the proton-neutron balance. The nucleus is not seeking balance with intention. It is simply following the allowed paths to lower energy. The language of a valley is a human image placed over quantum rules, but it is a useful image because it captures the direction of change. Nuclei do not decay randomly into any possible form. They decay towards states that the energy accounting allows. Some move quickly. Some move slowly. Some sit so close to stability that their decay takes longer than the age of the universe, if it happens at all. That slow edge of stability is one of the quietest places in nuclear physics. An isotope may be technically unstable and still endure for billions of years. Potassium-40, found in rocks and living tissue, decays with a half-life longer than 1 billion years. Other isotopes have half-lives so long that they seem nearly permanent beside human time. A nucleus can be unstable in principle and ancient in practice. The weak force may have an allowed path, but if the energy available is very small, the decay can be extremely slow. This changes the way stability feels. It is not a simple yes or no. There are nuclei that never appear to decay. There are nuclei that decay after moments. Between them are vast ranges of patience. The neutron sits at the center of much of this patience, because the number of neutrons determines whether the nucleus is too heavy on one side of the valley or close enough to the bottom to remain. The most stable nuclei are not always the most massive. Iron and nickel lie near the peak of binding energy per nucleon, the region where nuclear matter is held with unusual efficiency. Fusion of light elements can release energy by moving upward toward that region. Fission of very heavy elements can release energy by splitting and moving back toward it. This is why stars can shine by fusing light nuclei, and why heavy nuclei, such as uranium, can release energy when broken. Both processes are guided by the same curve of nuclear binding. Neutrons shape that curve from within. Without neutrons, complex nuclei would be torn apart by proton repulsion. A universe of only protons and electrons would have hydrogen, but little else stable enough to support the chemical richness seen in planets and life. The neutron allows nuclei to grow. It gives the periodic table thickness. It makes possible elements that require many protons by helping the nucleus carry them. Yet too many neutrons can also become a burden. Each added neutron must fit into the allowed quantum structure. When neutron states climb too high in energy, the nucleus becomes eager to shed the imbalance. Far from the valley of stability, in very neutron-rich nuclei, decay can happen rapidly. These short-lived isotopes may exist for fractions of a second in laboratories or in stellar explosions, then shift toward stability through chains of beta decay. There are limits even beyond that, known as drip lines. Past the neutron drip line, a nucleus cannot hold another neutron. The extra neutron is not bound. It drips away, not as liquid, but as an unheld particle outside the nuclear well. Past the proton drip line, the same idea appears for protons, though electric repulsion makes the proton-rich side different. These borders mark the edges of nuclear existence. Inside them, nuclei can be bound. Outside them, the attempted nucleus cannot keep all its pieces. In laboratories, physicists create rare isotopes near these edges, to learn how nuclear structure behaves far from ordinary stability. Many of those nuclei are too short-lived to exist naturally on Earth in any lasting amount. They appear, decay, and vanish. But in violent astrophysical environments, the same kinds of neutron-rich nuclei can be made in great numbers for brief times. Stellar explosions and neutron-star mergers push matter far from the quiet valley, then let it decay back toward it. The chart of nuclei becomes not just a diagram in a textbook, but a map of cosmic alchemy. This is where the valley of stability begins to point outward again. A neutron-rich nucleus made in a stellar event may not stay neutron-rich. It may undergo beta decay, turning neutrons into protons one by one. Each decay moves the nucleus to a different element. In a chain of such decays, matter climbs through the periodic table after first being loaded with neutrons. The final stable element may appear long after the first capture event, as the nucleus finds its way down through the slopes of the valley. The ordinary world is made mostly from nuclei that have already found that valley. Oxygen in water, carbon in organic molecules, calcium in bone, silicon in rock, iron in blood and planetary cores. These nuclei are not balanced by chance. They are the survivors of nuclear rules, the arrangements in which the strong force, the electromagnetic force, and the weak force have settled into a lasting compromise. Their neutrons are not free to decay because the whole nucleus gives them no lower path to follow. In that sense, every stable atom is a small agreement among forces. The strong force pulls, electromagnetism pushes, the weak force offers transformations, quantum rules decide which states can be occupied. Mass differences tilt the landscape, binding energy lowers the floor. The result, when the balance is right, is an atom that can sit quietly in a crystal, a drop of water, a grain of dust, or a living cell. The neutron remains central to that quiet. It does not carry charge, yet it gives weight and balance. It can decay when alone, yet it can preserve matter when bound. It can make a nucleus too rich, or make it stable enough to last through cosmic ages. It is both a source of instability and one of the reasons stability exists at all. The Valley of Stability is therefore not only a nuclear chart, it is the hidden geography beneath ordinary matter. The next step carries that geography back to the beginning, to the time when the first protons and neutrons had only minutes to decide the chemical starting point of the universe. Before the first stars, before the first galaxies, before any dust grain could drift through cold space, the universe is a bright, dense sea of particles and radiation. It is not yet the dark sky that later eyes will imagine. There are no constellations, no planets, no quiet spaces between suns. There is only expansion, cooling, and a fog of light so energetic that matter can barely begin to hold itself together. In that early brightness, protons and neutrons appear as the first stable pieces of atomic nuclei. They are not yet gathered into atoms. Electrons are not yet settled around nuclei. The universe is far too hot for ordinary chemistry, far too young for stars, and far too crowded for the calm architecture of matter. Still, the ingredients are there. Protons, neutrons, electrons, neutrinos, photons, all moving through a plasma that fills everything. At first, protons and neutrons can still change into one another. The weak force allows the exchange. A proton can become a neutron under the right conditions. A neutron can become a proton. Electrons, positrons, neutrinos, and antineutrinos are all part of the traffic that keeps the balance shifting. The universe is hot enough that energy is available for both directions. The difference between proton and neutron mass has not yet settled the outcome fully, because the surrounding radiation can help push reactions uphill as well as downhill. But expansion changes everything. As the universe grows, it cools. The particles spread farther apart. The reactions that once happened easily begin to slow. The weak interactions that keep protons and neutrons converting back and forth can no longer keep pace with the cooling. At a certain stage, the ratio begins to freeze. Not freeze as ice freezes, but freeze in the sense that the balance stops adjusting quickly enough to remain in perfect thermal agreement. The universe moves on, and the proton-neutron ratio is left behind as a record of that moment. Because the neutron is slightly heavier than the proton, protons become more common. The lower energy state wins as the heat fades. Neutrons remain, but fewer of them. And once the weak reactions fall out of balance, the free neutrons face their own quiet clock. They can decay. Every minute that passes removes some of them from the pool available to build nuclei. The early universe becomes a race between expansion, cooling, nuclear capture, and neutron decay. The race is not dramatic in sound. There is no explosion inside the plasma, no sharp boundary where matter suddenly becomes finished. There is only a changing set of conditions. A neutron that remains free too long may become a proton. A neutron that joins a stable nucleus may survive. The same rule that governs a lone neutron in empty space now shapes the chemical starting point of the whole cosmos. The first important step is deuterium. Deuterium is heavy hydrogen, a nucleus made of one proton and one neutron. It is the simplest bound partnership between the two nucleons. If deuterium can survive, it can act as a doorway to helium. More reactions can follow. Deuterium can combine with other nuclei. Helium-3, tritium, and then helium-4 can form. The universe can begin to lock neutrons into something stable. For a while, deuterium cannot survive. The early universe is full of photons, particles of light, and many of those photons still carry enough energy to smash deuterium apart almost as soon as it forms. A proton and neutron find each other, bind for a moment, and then a photon breaks the fragile nucleus back into separate pieces. The process repeats. Formation and destruction. Formation and destruction. The ingredients are present, but the heat keeps the first doorway from staying open. This delay is often called the deuterium bottleneck. It is a narrow passage in the first minutes of nuclear history. The universe must cool enough for deuterium to stop being broken apart faster than it can be used. Until that happens, heavier nuclei cannot form in large amounts. Neutrons wait in the plasma, and while they wait, some decay. The timing is delicate. If the universe cooled too slowly, more neutrons would disappear before being captured. Less helium would form. If the neutron lived much longer, more neutrons would survive into nuclei, and the first chemical mixture would be different. The amount of helium made in those first minutes is therefore tied to the neutron lifetime, to the strength of the weak force, and to the rate at which the universe expands. When the temperature finally falls enough, deuterium survives. The bottleneck opens. Nuclear reactions move quickly. Deuterium combines with protons and neutrons. Helium-3 and tritium appear. Helium-4 forms, and helium-4 is deeply stable. Two protons and two neutrons settle into a compact arrangement with strong binding. Once neutrons are placed inside helium-4, they are no longer doomed free particles. They are sheltered. A large fraction of the surviving neutrons end up there. The result is one of the oldest chemical facts in the universe. Most ordinary matter begins as hydrogen, with a smaller but significant amount of helium. A trace of deuterium remains. Tiny amounts of helium-3 and lithium form. But the first nuclear story is mostly hydrogen and helium, simple nuclei made before any star has ever burned. This first abundance still matters. When later astronomers observe old gas clouds, especially gas that has been little changed by generations of stars, they can compare the measured amounts of hydrogen, helium, deuterium, and lithium with the predictions from Big Bang nucleosynthesis. The agreement for helium and deuterium is one of the great quiet supports beneath modern cosmology. It says that the early universe was once hot and dense enough to make nuclei in a brief, measurable window of time. The neutron is written into that evidence. Its decay rate helps set how many neutrons remain available. Its ability to bind with protons makes helium possible. Its instability, when free, prevents the early universe from keeping too many neutrons outside nuclei. The chemical beginning is not only a story of temperature and expansion, it is also a story of a particle that has minutes to find shelter. After those first minutes, nuclear creation largely stops. The universe continues expanding and cooling, but the density falls too low for fusion reactions to proceed efficiently. There are no stars yet to provide new furnaces. There are no heavy elements in any meaningful amount. Carbon, oxygen, silicon, iron, and gold are still absent. The cosmos carries mostly hydrogen and helium, with traces of a few light nuclei, waiting in the darkening plasma for gravity to gather matter into the first stars. Only much later will stars take over the work. Gravity will pull gas into clouds. The clouds will fragment and collapse. Cores will heat. Fusion will begin. Hydrogen will become helium in stellar interiors, and in later generations of stars, heavier elements will be formed. But the first supply of helium does not come from stars. It comes from the early universe itself, from a narrow period when neutrons and protons could still meet before the free neutrons faded away. There is a quiet connection here between the smallest clock and the largest history. A neutron's lifetime is measured in minutes. The age of galaxies is measured in billions of years. Yet the first number helps shape the second environment. Galaxies form from gas, whose first composition was set by those minutes. Stars ignite in material already carrying the imprint of neutron survival. The long future begins with a short race. The early universe also shows why stability is never isolated from setting. A free neutron in that plasma is vulnerable. A neutron inside helium-4 is protected. The laws are the same, but the surroundings change what the laws allow. In empty space, the neutron can roll downhill into a proton. In helium, the decay would require a nuclear rearrangement that does not lower the total energy. The particle becomes safe because it belongs to a bound system. That is the same lesson seen inside ordinary atoms, now written across the whole beginning of cosmic chemistry. Context changes fate. The neutron alone is temporary. The neutron bound into helium becomes part of a nucleus that can cross cosmic ages. Many of those helium nuclei formed in the first minutes still drift through the universe today, inside stars, in interstellar gas, and in the atmospheres of giant planets. Their neutrons have outlived the early fire that saved them. The universe cools further. Light continues to scatter from free electrons for a much longer time, keeping space opaque until atoms finally form. But the nuclear part of the story has already taken its first shape. Hydrogen waits. Helium waits. A few light isotopes remain as small clues from the beginning. The neutron has done its first cosmic work. Later, inside stars, the same weak force that allowed neutron decay will become part of a slower and steadier process. It will allow hydrogen to burn gently instead of all at once. It will make starlight patient. The particle that had only minutes in the early universe will help make suns that shine for billions of years. Long after the first helium has formed, the universe enters a darker patience. Hydrogen and helium drift through expanding space. Gravity begins its slow gathering. The first clouds grow uneven. Slightly denser regions pull more material toward themselves, and over time, the quiet pull becomes a collapse. Gas falls inward. The center grows hotter. Pressure rises. The first stars begin as weight, darkness, and compression. A star is born when gravity squeezes matter until nuclear reactions can begin. In the core, protons move fast enough to approach one another despite their electric repulsion. Each proton carries positive charge, so two protons do not naturally want to touch. Electromagnetism pushes them apart, but in the dense heat of a stellar core, some pairs come close enough for quantum tunneling to matter, allowing them to slip through a barrier they could not climb over in ordinary classical motion. Yet closeness is not enough. Two protons alone do not simply become a stable helium nucleus. The first step in the proton-proton chain, the main fusion pathway in stars like the Sun, requires one of those protons to become a neutron. A deuterium nucleus must form, made of one proton and one neutron. That means a particle identity has to change. One of the proton's up quarks must become a down quark. A positron and an electron neutrino are emitted. The weak force has to act. This is the slow gate in the heart of the Sun. The strong force would bind a proton and neutron readily once the deuterium nucleus exists. The electromagnetic force shapes the charged particles. Gravity supplies the pressure that brings them close. But the weak force decides how often the necessary transformation happens. It is rare. It is slow. It does not occur every time two protons meet. Most encounters in the solar core end without fusion. The protons pass, scatter, and continue moving through the hot plasma. That failure is what saves the star from burning too quickly. If the strong force alone controlled the first step, the Sun would exhaust its hydrogen in a brief and violent blaze compared with its present life. Instead, the weak force turns the process into a narrow passage. Only a small fraction of suitable proton encounters produce deuterium. Once deuterium forms, later steps proceed much more quickly. Deuterium can fuse with another proton to form helium-3. Two helium-3 nuclei can combine to make helium-4, returning two protons to the plasma. But the opening step remains slow, and the whole star's pace is set by that slowness. The Sun shines because the weak force is weak. This is a gentle reversal of expectation. A force named for weakness seems, at first, like a minor actor beside gravity and the strong force. Yet the long life of ordinary stars depends on it. The weak force does not provide the star's light directly. It regulates the first conversion that lets hydrogen become helium in a stable way. Its reluctance becomes a kind of cosmic metronome, slowing the burning of stellar fuel until a star can shine for billions of years, instead of vanishing in a short outburst. In the solar core, the conditions are immense by earthly standards. Temperatures reach millions of degrees. Matter is pressed into plasma, with electrons stripped from nuclei. Particles move and collide constantly. Still, even there, the weak step is rare. A single proton in the core may wait an enormous time before it participates in fusion. The Sun as a whole shines brightly only because it contains so much matter that even rare events become abundant when multiplied across the deep core. The star is patient because probability is patient. Each second, vast numbers of protons take part in the chain that turns hydrogen into helium. Energy leaves the core first as radiation and motion, then wanders outward through layer after layer of solar material. A photon born in the core does not fly straight to space. It scatters again and again, changing direction through the dense interior. The journey outward can take a very long time before the energy finally reaches the surface and escapes as sunlight. By the time that light crosses space and warms a planet, the first weak interaction that made it possible is hidden far behind it. No trace in the yellow-white glow reveals the rarity of the proton's transformation into a neutron. The sunlight seems steady, ordinary, almost simple. Beneath it is a chain of balances: gravity pressing inward, pressure pushing outward, electromagnetism resisting close approach, quantum tunneling allowing proximity, the weak force changing identity, the strong force binding the result. A star is a compromise held in light. The neutron's role in this process is different from its role in the early universe, but the connection remains clear. In Big Bang nucleosynthesis, neutrons had to survive long enough to be captured into helium. In the Sun, neutrons are made as needed, briefly appearing inside deuterium and then moving onward into helium through fusion. They are not free for long. They are born into binding. The weak force creates the neutron condition, and the strong force quickly shelters it inside a nucleus. Again, solitude is avoided. The deuterium nucleus, formed in the Sun, is not deeply abundant because it is consumed quickly once it appears. It is a stepping stone, a short-lived bridge in the fusion chain. But without that bridge, the chain would not begin. Hydrogen would remain mostly hydrogen. The core could be hot and dense, gravity could be relentless, and still the long, steady conversion into helium would be blocked. The weak force opens the path just enough. This makes the weakness of the weak force one of the reasons worlds have time. Stars with long, stable lives give planets long, stable conditions. Around such stars, Dust can gather into rocky bodies. Surfaces can cool. Atmospheres can change. Chemistry can proceed through slow cycles. In at least one place, life can take advantage of billions of years of steady energy. The slowness in the core becomes time on a planet. The point does not require sentiment. It is only the consequence of rates. If fusion were much faster in sun-like stars, stable eras would be shorter. If the weak interaction behaved differently, stellar lifetimes, element production, and the structure of stars would change. The universe visible today depends not only on which reactions are possible, but on how often they occur. A reaction that happens too easily can exhaust its fuel. A reaction that never happens leaves the star dark. The sun exists in the middle, where rarity and abundance meet. A few particles decide the pace, but the pace belongs to the whole star. Neutrinos carry part of this hidden story away. In the proton-proton chain, electron neutrinos are produced when a proton becomes a neutron. Unlike light, they do not spend long ages scattering through the sun. They pass through the solar material almost unhindered, leaving the core within moments and crossing space with little interruption. Detectors on Earth can catch a tiny fraction of them, confirming that weak reactions are taking place deep inside the sun right now. The light from the surface tells of energy that has wandered outward. The neutrinos tell of the core almost directly. For many years, measurements of solar neutrinos revealed fewer than early models predicted, creating the solar neutrino problem. The answer did not lie in a failing sun, but in the nature of neutrinos themselves. Neutrinos change flavor as they travel, shifting among electron, muon, and tau forms. This showed that neutrinos have mass, however tiny, and that the weak force was again pointing toward a deeper structure beneath an apparently simple process. The sun became a laboratory for particle physics, and particle physics became part of astronomy. The neutron is not always present as a free object in this story, but the neutron-making transformation is essential. A proton becomes a neutron through the weak force, and the star's long burning becomes possible. The same force that lets a free neutron die lets a star live slowly. The direction changes with the energy landscape. In one setting, a neutron turns into a proton. In another, a proton becomes a neutron inside a newly forming deuterium nucleus. The weak force does not favor a story. It follows what the conditions allow. The quietness of the process fits the quietness of starlight seen from far away. A star appears as a point in the night, steady enough that generations can give it a name. Inside, however, the star is a deep engine of pressure, plasma, and nuclear conversion. Its calm appearance is another average, another surface made by many hidden motions. Like the neutron, it looks simpler from a distance than it is within. The path now moves toward stars that do not remain gentle. Sun-like stars make helium slowly, and later leave behind quieter remnants. More massive stars go further. Their cores grow hotter. They build heavier nuclei in shells, carbon, oxygen, neon, silicon, and finally iron. At iron, fusion no longer gives the same outward gift of energy. The balance begins to fail. Gravity waits beneath the structure. When such a star dies, neutrons return in overwhelming numbers. The slow work of the weak force gives way to collapse, compression, and neutron-rich matter. The next chamber of the story is no longer the steady light of a sun, but the dark remnant left when a massive star's core is forced beyond ordinary matter. When a massive star approaches the end of its life, its center becomes a place where ordinary descriptions lose their footing. For millions of years, gravity has pressed inward, while nuclear reactions have pushed back. Lighter elements have fused into heavier ones. Hydrogen has become helium. Helium has become carbon and oxygen. In the deepest layers of the most massive stars, the chain continues through neon, magnesium, silicon, and finally, iron group nuclei. Iron changes the story. Fusion up to iron can release energy, feeding the pressure that helps a star stand against its own gravity. Beyond iron, fusion no longer pays the same energy debt. It begins to cost energy rather than release it. The core fills with matter near the end of the nuclear road, and the old balance grows fragile. The star still has mass above the core. Gravity still pulls, but the central engine can no longer find an easy source of outward support. The collapse begins in the core, not as a visible fall from the outside, but as a failure of pressure at the center. Electrons, once helping to resist compression through quantum rules, are pushed into protons. The weak force enters again. A proton and an electron combine to form a neutron and an electron neutrino. This process is called electron capture. It turns charged matter into neutron-rich matter, and it sends enormous numbers of neutrinos outward from the deepening collapse. The star is making neutrons by crushing charge away. As the core contracts, matter reaches densities far beyond anything in ordinary planets or laboratories. Atomic nuclei are pressed closer and closer together. Electrons are driven into protons. Neutrons multiply. The collapse accelerates until the core reaches nuclear density, the density where matter is packed almost as tightly as the matter inside atomic nuclei themselves. At that point, the inner core stiffens. It cannot be compressed easily in the same way. The collapse rebounds, and the outer layers of the star are eventually thrown outward in a supernova. What remains can be a neutron star. The name is simple, but the object is not. A neutron star is not a single enormous atomic nucleus, though it is sometimes described that way to give a first feeling for its density. It is a stellar remnant whose matter has been forced into states where neutrons dominate, but where the structure varies from surface to center. It is a city-sized object with more mass than the sun squeezed into a sphere far smaller than any familiar astronomical body. The surface gravity is so strong that height, shape, and motion take on meanings unlike anything on Earth. Near the surface, the matter may still contain ordinary nuclei, though they are arranged in a rigid crust under immense pressure. Deeper down, those nuclei become more neutron-rich. Electrons are packed into a dense quantum sea. Free neutrons begin to appear outside nuclei once the neutron drip point is reached. The phrase sounds almost liquid, but it refers to a nuclear boundary. Beyond a certain density, nuclei cannot hold all their neutrons, and some neutrons become part of a wider neutron fluid. There, the old idea of a neutron inside a neat atom has already broken open. The neutron is no longer simply one particle sheltered in a nucleus. It becomes part of a collective form of matter. Many neutrons move through the crust, affected by quantum rules, nuclear forces, and the immense pressure of the star. Some may form a superfluid, a state in which matter flows without ordinary viscosity. In a neutron star, superfluid neutrons are not a laboratory curiosity cooled in a vessel. They are part of a dead star's interior, shaped by gravity and nuclear physics together. Still deeper, the nuclei themselves may distort. Under crushing pressure, round nuclei are no longer always the lowest energy arrangement. Nuclear matter may stretch into rods, slabs, tubes, and complex shapes. Physicists call these possible structures nuclear pasta, using names borrowed from familiar food, because the shapes in simulations can resemble spaghetti, lasagna, and other layered forms. The names are almost gentle. The reality is not culinary at all. It is matter pushed into strange geometry by the competition between nuclear attraction and electric repulsion. This nuclear pasta, if present, would live in the deep crust of neutron stars, near the boundary where distinct nuclei give way to more uniform nuclear matter. The strong force tries to pull nucleons together. Electromagnetic repulsion among protons resists certain arrangements. Neutrons flood the system. Gravity keeps pressure rising from above. The result may be matter shaped into long filaments, flat sheets, connected networks, or hollow phases, all at densities that make ordinary solids seem almost empty. It is one of the hidden forms of matter in the universe. The neutron story has changed scale again. In a free particle, it had minutes. Inside a stable nucleus, it could survive for cosmic ages. Inside a neutron star, Neutrons are part of a remnant where the idea of individual atomic identity begins to fade. Carbon and oxygen, iron and silicon, all the familiar names of chemistry are no longer the right language for the deepest layers. Matter is organized by pressure, density, and quantum state more than by ordinary elements. Neutron stars also rotate. Many are born spinning rapidly, carrying angular momentum from the collapsing core. Some are seen as pulsars, sending beams of radiation across space like lighthouse sweeps. The pulses are not the sound of the star, and they are not signals in the intentional sense. They are the result of rotation, magnetic fields, and radiation from a compact remnant. Each pulse that reaches Earth is a timed trace of extreme matter turning in darkness. Inside such a star, the neutrons may not rotate as one perfectly locked body with the crust. Superfluid components can store angular momentum differently. In some pulsars, sudden jumps in rotation called glitches may be linked to interactions between the crust and the superfluid interior. The star turns steadily, then suddenly a little faster, as if some hidden reservoir of motion has shifted. The surface timing becomes a clue to the interior. A neutron star cannot be opened. Its deep matter cannot be placed on a table. The evidence comes indirectly, through mass measurements, pulse timing, X-ray emission, gravitational waves, cooling behavior, and the way such stars respond when they are disturbed. This is often how astronomy works. The object remains far away, but its behavior carries the imprint of what it must be made of. Recent observations have made neutron stars especially important for understanding dense matter. Some neutron stars have been measured with masses around twice the mass of the Sun, which tells physicists that the matter inside must be stiff enough to resist collapse into a black hole at those masses. X-ray measurements of neutron star sizes give further constraints. Gravitational waves from neutron star mergers reveal how easily the stars deform under each other's gravity before they collide. Each observation narrows the possible forms of matter inside. The neutron, once introduced as the quiet, neutral partner in the atom, has become a probe of physics that no Earth laboratory can fully reproduce. There may be more than neutrons in the deepest core, depending on the true equation of state, the relation between pressure and density inside the star. The center might contain exotic particles, hyperons, meson condensates, or even deconfined quark matter. None of these possibilities can be stated as settled for all neutron stars. The honest answer is that the interior remains partly unknown. What is known is enough to make the remnant one of the most severe tests of matter in the universe. The uncertainty fits the theme. At every scale, the neutron resists becoming a simple object. It is not a featureless neutral bead. It is not merely a decaying particle. It is not only a stabilizer of nuclei. Under gravity's most intense pressure outside a black hole, neutron-rich matter becomes a landscape of possible phases, superfluids, crusts, pasta layers, and cores whose final nature is still being worked out. A dead star keeps that question. The supernova that creates a neutron star also throws enriched material outward. Around the compact remnant, expanding debris carries newly formed and reshaped nuclei into space. Some of that material will cool into future clouds. Some will be stirred into later generations of stars and planets. The remnant itself remains behind, small, dense, and dark, except for the radiation its magnetic fields and heat may release. The neutron has entered its most compressed home, not the shelter of an ordinary nucleus, but the crushing shelter of a stellar corpse. In that place, the same particle that cannot survive alone becomes part of matter so dense that a small volume would outweigh mountains. The path now leads from one dead star to two, from isolated neutron matter to collision, where the breaking open of neutron-rich remnants can flood space with the raw material for some of the heaviest elements in nature. When two neutron stars orbit one another, the space between them is not empty in the ordinary sense. Gravity has already shaped it into a tightening path. Each star pulls on the other with a force so strong that their surfaces rise and deform, not like oceans under a moon, but like dense nuclear matter answering curvature itself. They are small by stellar standards, but they carry more mass than the Sun. Their dance can continue for millions of years, losing energy through gravitational waves, tiny ripples in space-time moving outward at the speed of light. The orbit shrinks, slowly at first, then faster. Near the end, the two remnants whirl around each other hundreds of times each second. Their gravity stretches them, their crusts strain. Matter at densities beyond atomic nuclei is pulled into motion. The final collision is not a simple impact between solid objects. It is the meeting of two bodies made from extreme matter, with neutron-rich material torn loose and thrown into space. Some of the merged mass may collapse into a black hole. Some may form a hot, short-lived disk. Some escapes. That escaped matter carries neutrons in abundance. Here the neutron's old instability becomes part of a larger making. Free neutrons decay when left alone for long enough. But in this debris there are so many neutrons, moving through such dense and violent conditions, that atomic nuclei can capture them rapidly. A nucleus may absorb one neutron, then another, faster than beta decay, can turn those neutrons into protons. This is the rapid neutron capture process, often called the R process. It is one of the main ways the universe builds many of the heaviest elements. The process begins with seed nuclei, atomic nuclei already present in the ejecta. In a neutron-rich flood, these seeds capture neutrons again and again. Each capture increases the mass of the nucleus without changing the element, because a neutron adds no electric charge. But the nucleus becomes more and more neutron-rich, pushed far away from the valley of stability. It cannot remain there forever. Beta decay follows. Some neutrons inside the overfilled nucleus transform into protons, and each transformation raises the atomic number. The element changes. Step by step, capture and decay move matter upward through the periodic table. This is not ordinary chemistry. Electrons are not being shared between atoms. Molecules are not forming. It is deeper than that. The identity of the nucleus itself is being rewritten by neutron capture and weak decay. Gold, platinum, uranium, and other heavy elements can be assembled through these paths, not by slowly adding charged protons, which would be blocked by electric repulsion, but by adding neutral particles first and allowing the weak force to change some of them later. The neutron enters quietly because it has no charge. That neutrality is its key. A proton trying to enter a heavy nucleus must push against positive charge already present. A neutron can slip into the nuclear force without feeling that electric wall. Only after capture, after the nucleus has been loaded with extra mass, does beta decay raise some neutrons into protons. The element climbs because neutrality made the first step possible. There is also a slower neutron path in the universe. In aging stars, especially certain giant stars late in their lives, nuclei can capture neutrons at a gentler pace. This is the slow neutron capture process, or S process. In that setting, a nucleus usually has time to beta decay before it captures another neutron. The path stays closer to the valley of stability. It builds many heavy elements gradually, over stellar lifetimes, inside stars that shed enriched material back into space through winds. The R process is different. It runs far from stability, in conditions where neutrons arrive faster than the nucleus can settle. For a long time, physicists knew the process was needed because the pattern of heavy elements demanded it. The question was where nature provided enough free neutrons. Core collapse supernovae were considered strong candidates. They may contribute in some cases, but neutron-star mergers offer an especially rich site because they begin with matter already saturated with neutrons. In the year 2017, the signal named GW170817 reached Earth. Gravitational wave detectors recorded the final in-spiral of two neutron stars. Telescopes across the world and in orbit then saw light from the same event. It was the first time a neutron-star merger was observed through both gravitational waves and electromagnetic radiation. The light that followed was a kilonova, powered by radioactive decay in freshly made heavy nuclei. The color changed as the debris expanded and cooled. Blue light appeared early from faster, less opaque material. Redder infrared light followed, as heavier R-process elements affected how radiation escaped. The glow faded, but while it lasted, it carried evidence that neutron-rich mergers can manufacture heavy elements in great amounts. Matter forged in the collision was shining as it decayed toward stability. This is a return to the valley on a cosmic scale. The merger throws nuclei far from stable arrangements. Neutrons are captured in rapid succession. The nuclei become overloaded, strange, short-lived. Then beta decay pulls them back, one step at a time, toward longer-lived forms. The light of the kilonova is partly the heat of that settling, the energy released as unstable nuclei find lower states. The neutron's role is both temporary and lasting. As a free particle, it cannot drift forever. In the R process, it may be captured before it decays. Once captured, it may remain a neutron inside a new nucleus, helping stabilize it. Or it may later turn into a proton, changing one element into another. Its instability is not only a weakness, it is a tool nature uses to move between elements after neutral mass has been added. The same pattern has appeared again and again. A neutron alone changes. A neutron bound can endure. A neutron captured rapidly can help build a heavy nucleus that did not exist before. A neutron converted by beta decay can move that nucleus to a new place on the periodic table. The particle is small, but its allowed transformations give matter a route through otherwise difficult terrain. Heavy elements are rare compared with hydrogen and helium. The universe is still mostly simple. Most atoms are hydrogen. Much of the rest is helium. But the small fraction of heavier material changes everything. Carbon allows complex molecular chains. Oxygen binds with hydrogen into water, and with silicon into rock. Phosphorus becomes part of genetic chemistry. Iron carries oxygen in blood and gathers in planetary cores. Elements heavier still form minerals, catalysts, radioactive heat sources, and metals, whose presence records the deaths and collisions of stars. Gold does not form because it is precious. It is precious partly because the path to form it is demanding. It requires neutron-rich conditions, rapid capture, decay chains, and violent astrophysical sites that do not happen everywhere. A ring on a hand, a thin wire in an instrument, a trace of platinum in rock, all carry the memory of nuclei that once moved through neutron fire. The phrase is an image, not a flame in the ordinary sense. In a kilonova, the fire is nuclear and radioactive. It is the glow of matter rearranging itself after being torn from dead stars. It is neutron-rich debris, becoming less unstable, releasing energy as it moves toward forms that can last. The light fades in days and weeks. The atoms remain. Those atoms travel. They mix into interstellar gas. They become part of molecular clouds. Later generations of stars form from such clouds, and around some stars, disks of dust and gas gather into planets. The heavy elements settle into minerals, oceans, atmospheres, and living systems. The path from neutron capture to biology is long, broken, and without intention, but it is physically continuous. Matter made in stellar death becomes matter available for worlds. The neutron is one of the links across that distance. It belongs to the first minutes after the Big Bang, where its survival helps set the helium abundance. It belongs to the cores of stars, where weak transformations allow steady burning. It belongs to stable nuclei, where binding energy protects it. It belongs to neutron stars, where dense matter presses it into states beyond ordinary atoms. It belongs to collisions, where a flood of neutrons helps build elements heavier than iron. The journey has moved from the center of an atom to the meeting of dead stars, then back again to ordinary matter. A quiet object in the nucleus turns out to be part of a larger rhythm of capture, decay, binding, and release. Its fate depends on context, and the universe is made of contexts layered upon one another. A free neutron has minutes. A neutron in helium can last through cosmic ages. A neutron in a star may be born at the gateway of fusion. A neutron in a merger may enter a nucleus that becomes gold. The particle is never only itself. It is always part of a field, a nucleus, a star, a remnant, a cloud, a planet, a body. At the end of the path, ordinary matter looks less ordinary. The calm weight of the world contains strong fields. The atoms of the body contain ancient neutrons. The heavy elements in stone and blood carry traces of stellar burning and stellar death. Nothing has to be loud for that to be true. The evidence is already inside the matter that remains. The neutron's path fades back into quiet matter. The collisions are far away now. The first fire of the universe has cooled beyond sight. The cores of stars are hidden behind their steady surfaces, and the dead remnants drift in darkness, holding their dense secrets without sound. What remains nearby is ordinary and calm. A room, a surface, a breath, the soft weight of the body resting in the present moment. Inside that weight are atoms whose nuclei have carried their neutrons through long histories. Some were shaped in the first minutes of cosmic time. Some were made and remade in stars. Some passed through clouds of gas and dust before becoming part of a planet, and later part of living matter for a while. Nothing in them needs to hurry now. The forces continue their hidden work at scales too small for thought to hold for long. The strong force binds, the weak force waits. Binding energy shelters what can be sheltered. The old balance remains, quiet beneath skin, stone, air, and water. Matter does not need to explain itself in order to stay. Beyond the walls, the night sky keeps its distance. Stars shine with slow patience. Somewhere, gas gathers. Somewhere, a remnant cools. Somewhere, atoms made in an ancient collision drift through space without destination, carrying neutrons that have found their place. The story can be left there, not finished in the sense of being closed, but softened enough to rest. The smallest particles continue without attention. The universe continues without strain. And for now, the mind can let go of the details and keep only the feeling of a vast, quiet structure, holding together in the dark.